All right, now problem number 3 says we got a student standing on a smooth surface, and they use a stick to push a disk of mass m sub d. Student exerts a constant force, magnitude f sub h, over a time interval from t equals 0 to t equals t sub f while pushing the disk. And assuming there's negligible friction between the disk and the surface. So it also says that the surface is smooth, which you can assume then that, you know, you don't know if there's friction between the student's feet and the surface or not. Just because a surface is smooth does not necessarily mean that there is friction or not. For instance, you could say that the floor in a classroom with a hard floor is smooth, but you still have plenty of friction between your feet and the surface. So it says that there's friction between the disk and the surface. But it turns out it doesn't really make a whole lot of difference in this problem. So there's a student, they're standing here, they have some kind of stick, maybe it's like shuffleboard, and there's a disk that's sitting on the surface. And the student exerts a force on the disk. And that force is S sub h to be a horizontal force. The reason why it doesn't matter if the student moves or not is that for every action, there's an equal and opposite reaction. The force on the disk and the force on the student are exactly the same, but there's force that's for some period of time. This problem kind of suggests you should think about the impulse momentum theorem. The impulse momentum theorem generically is F delta t is equal to m delta v. In terms of the variables that are defined in this problem, the force is F sub h, the t that is t sub f, m in this case is the mass of the disk, so the mass of the disk times the final, or times the change in speed, and the change in speed if it begins from rest is equal to v sub d. So we want to determine an expression for the final speed of the disk relative to the surface in terms of f sub h, t sub f, m sub s, m sub d, and any physical constants, which could include gravity, could have some kind of constant of some kind, but we want v sub d. So v sub d is equal to f sub h, t sub f divided by m sub d. And that is it. There's nothing else. The mass of the person is irrelevant. There are no other physical constants, but we satisfied the problem where we defined an expression for v sub d, make it look like a lowercase v, in terms of f sub h, t sub f, and m sub d. So that's it. Assuming there's negligible friction between the student's shoes and the surface. After time t sub f, the student slides with a speed v sub f. Now it's very important to notice it says speed and not velocity. So the variable v could be speed or velocity. Derive an equation for the ratio v sub d to v sub s. Express your answer in terms of m sub s, m sub d, and physical constants as appropriate. Now that we know that the student actually slides, the student will go in this direction, and the disk goes in that direction. According to the law of conservation of momentum, the initial momentum must equal the final momentum, and the initial momentum in the problem before pushing is equal to 0. So the final momentum is equal to the momentum of the student plus the momentum of the disk. Or another way to look at it, because the momentum of the student is negative, this actually has a negative velocity, and the disk has a positive velocity. The momentum of the student, which is negative, plus the momentum of the disk, which is positive, must have the same magnitude but be opposite in sign. But because this problem is just in terms of speed, you can make it even simpler and just say that the momentum of the student is equal to the momentum of the disk in terms of their speeds. The momentum of the student is equal to the mass of the student, I guess that's a capital M, mass of the student times the velocity of the student, and that's going to be exactly equal to, or not the velocity, but the speed of the student. The momentum of the disk is equal to the mass of the disk times the speed of the disk. So because these are speeds, you don't have to worry about signs at all. We want to derive an equation for the ratio v sub d over v sub s. So v sub d over v sub s, if I divide both sides by v sub s and divide both sides by m sub d, I get the expression v sub d over v sub s is equal to m sub s over m sub d. just like that. There's no need for positive or negative signs because the problem says it's in terms of speed. Now, if it were to be in terms of velocity, it would be appropriate to make one of the velocities negative and one of the velocities positive, because the value that you would substitute would be positive for the disk and negative for the student in the case of the diagram that I drew. But that would be it. That's the answer in the box. Okay, assume that the student's mass is greater than that of the disk. On the grid below, sketch graphs of the speed of both the student and the disk as a function of time between t sub naught and t sub 2 tf, which is twice the time that the interaction takes place for. Okay, the student pushes on the disk during the time t sub f. So if this is the disk, the pushing takes place during the time equal to some time t sub f. Assume that neither the disk nor the student collides with anything after t equals t sub f. So while the student is pushing on the disk, both the student will accelerate to the left and the disk will accelerate to the right. But after the student and the disk are free of each other, the student and the disk should travel along at a constant speed. The change in speed for the disk is going to be greater than the change in speed for the person, because the ratio of their masses is different, and it defines that the student's mass is greater than that of the disk, which you would assume unless the disk were to be an incredibly massive disk, but it sounds more like shuffleboard, so that's all good. The y-axis has speed, but doesn't say anything about what the scale is, and you don't know what the scale of the ratios of the masses are. So here I'm just going to make up some kind of call this the final speed for the disk, and I'll make the final speed for the person maybe like up here. And although they're moving in opposite directions, so that one would have a positive velocity, the other one would have a negative velocity, because the y-axis says speed and not velocity, there are no negative values. It's just a scalar quantity. All right, so here's how I would do the graph. I'd say here, this represents the motion of the disk whenever the disk is accelerated for time t sub f, or the student, and this would represent the increase in speed for the disk during time t sub f. And then after the interaction takes place, the speed of the disk is constant and the speed of the student is constant. So just like that. And it really doesn't matter where you put them relative to each other, but we must label the axes. So on the vertical axis, label v sub d and v sub s. We'll call this v sub d, and I'll make this v sub s. So why the graphs look like this is the slope on a velocity time graph is equal to the acceleration. That's because acceleration is equal to delta v over delta t. So the rate of acceleration of the disk during the pushing is greater than the rate of acceleration of the student during the pushing. Or you can also know that the final velocity of the disk is large compared to the final velocity of the student. And you can even see that because, here, I'll just copy this in. Oops, didn't want to do that. This ratio here, let's see if I can get just that. I guess I can't. I'll copy this whole thing, put it in here, paste that, but I need to get rid of this thing. Okay, so the ratio of the velocity of the disk to velocity of the student is greater than 1 when the ratio of the mass of the student to the mass of the disk is greater than 1, which it is in this case. So because the speed of the student doesn't change after the interaction and it's on a frictionless surface, the speed of the student is constant from time tf to time 2tf, and the speed of the disk is constant from time t sub f to 2t sub f. It doesn't matter where these are on the vertical axis. They don't have to come up to here. You can make the disk, come up to here and then go straight across if you want. In this case, the student has 4 times as much mass as the disk, but it really doesn't make a difference what the vertical scaling is, so long as v sub d is above the d sub s, or the v sub s. You could have these 2 points, or these 2 points on t sub f relatively close to each other, so long as v sub d is some value that's greater than v sub s. So that looks pretty good. Now, the disk is moving at a constant speed on a surface toward block mass m sub b. So the student's all done with it now. The disk is just moving along. The disk and the block collide head-on and stick together. That they stick together means that the collision is an inelastic collision. So we know that it's inelastic. And that makes the math a little bit easier. In the center mass, the disk block system moves with the speed vc sub m. Suppose the mass of the disk is much greater than the mass of the block. Estimate a velocity for the center mass of the disk block system. Explain how you arrive at your prediction without deriving it mathematically. Well, what you might do conceptually is think about what happens in the collision as an aside. So here I've got the mass of the disk times the velocity of the disk, and it's going to collide with the block. And the block has no momentum initially. After the collision, when the collision takes place and they stick together and move together, you have the mass of the disk times, or plus the mass of the block, times the velocity afterwards, which in this problem is defined as v c sub m. So this mass of the disk times the velocity of the disk before the collision takes place is exactly equal to the sum of the masses of the disk and the block times the velocity afterward. That's a very basic law of conservation of momentum problem. So if the mass of the disk is greater than the mass of the block, what's the velocity of the center of mass of the disk block system? You would say that the velocity of the center of mass of the disk block system is like just less than the velocity of the disk before the collision takes place. So arrive at your prediction without deriving it mathematically. I mean, you can sketch this on the side to think about it if you want. In the end, the velocity of the center mass of the system is equal to the mass of the disk times the velocity of the disk initially, divided by the sum of the mass of the disk and the mass of the block. It's good to rely upon a mathematical description, but your explanation is not based upon deriving it mathematically. What you'd want to say is that because of the law of conservation of momentum, the momentum before the collision and the momentum after the collision are exactly equal. If the mass of the disk is very large as compared to the mass of the block, the mass of the system does not increase appreciably, and therefore the velocity of the system does not decrease appreciably, but it would decrease by some amount. Suppose the mass of the disk is much less than the mass of the block. Estimate the velocity of the center mass of the disk block system. The velocity of the center of the mass, you could say, is just above 0. If the mass of the disk is much less than the mass of the block, the mass of the system increases significantly, so the velocity of the center of the mass of the system must decrease significantly, not become 0, but become some value that's close to 0. Now suppose that neither object's mass is much greater than the other, but they're not necessarily equal. Derive a velocity for v sub cm. Express your answer in terms of both v1, m sub d, m sub b, and physical constants as appropriate. So that's the derivation that I did. And there's no reason why you can't do that derivation in advance in order to help you understand the concept, but that derivation has nothing to do with the explanation. So, and I didn't write out full explanations, but you get a little bit of space to write a couple sentences. Here, your answer in terms of v1, m sub d, m sub b. So v sub cm is equal to m sub d times v sub 1 over m sub d plus m sub b. That's the expression. If you want to put the denominator in parentheses, you can do it. That's fine. It doesn't really make a whole lot of difference. But that's the derivation of the expression. So that's it. That problem's not so bad. It's not like a full paragraph, just some quick explanations. So then part 4 of that problem says to consider the scenario from part C1 where the mass of the disk is much greater than the mass of the block. Does your equation for V sub Cm from part 3 or part C3 agree with your reasoning from part C1? So that's kind of a lot to refer to, but this is the derivation of the expression that I came up with. So let me copy that into here. And your goal is to say, how does this expression relate to what your conclusion was from the from your explanation from before? So in a way, you kind of qualitatively described it, and now you get a chance to quantitatively describe the expression or the deal. So it turns out that yes, you can justify your answer. So based upon this problem, if m sub d is much greater than m sub b, you really have a ratio here of m sub d over m sub d plus m sub b. This expression can be written slightly differently as m sub d over m sub d plus m sub b times v1. Really, the final velocity of the center of mass of the system is directly proportional to v sub 1 and directly proportional to the ratio m sub d over m sub d plus m sub b. If m sub d is much greater than m sub b, then this ratio m sub d over m sub d plus m sub b approaches 1 when m sub d is much greater than m sub b. You could even make up numbers if you feel like. Let's say that the mass of the disk is 1,000 kilograms, and then it's 1,000 kilograms plus maybe 2 kilogram. Now you have the ratio 1,000 to 1,002, and that ratio is pretty close to 1. It's not 1, but it approaches 1. And as this ratio of the m sub d over m sub d plus m sub b approaches 1, v sub cm approaches v sub 1. V sub cm is always going to be less than v sub 1, but v sub cm is pretty close to v sub 1.